Hi, and welcome to part 3 of lecture 24. So in parts 1 and 2, we talked about the characteristic polynomial of a linear transformation or a linear map. And to this part, we want to introduce what's called the minimal polynomial. So the first thing that we need to do is define what we mean by a monic polynomial. So a polynomial is monic if the highest degree coefficient is 1. Okay, so what that means is when you write your polynomial, and let's say that its degree is n, the coefficient of z to the n is 1. And then the other coefficients are allowed to be anything that you want. Okay, so the key thing is that the coefficient at the front is a 1. So the next theorem here we're going to need in order to define what we mean by the minimal polynomial. So the theorem says that if I take any linear operator, then there's a unique monic polynomial of smallest degree such that I can plug t into my operator and get the zero operator. Okay, so the Cayley-Hamilton theorem says that there is a polynomial with this property. This theorem says there's actually a unique smallest one. Okay, so let's walk our way through the proof. Okay, and I've kind of left some gaps here to fill in the pieces. So if n is the dimension of V, then the dimension of this space of linear operators is equal to n squared. This is kind of going back to chapter 3 material. Now what we're going to do is we're going to consider the operators, a whole sequence of operators. And these operators we're going to consider are I, t, t squared, t cubed, all the way up to tn squared. And all of these guys live inside of the space of linear operators. Okay, so that's not too surprising. Now, since the dimension of this space is n squared, and we have n squared plus 1 operators, right? Hopefully you can see that we have n squared plus 1 because you start your counting at 0. So 0, 1, 2, 3 up to n squared. Because this is a vector space, we have more operators than the dimension. They have to be linearly dependent. Okay, so there's some sort of linear combination of these that give you 0. So what we're going to do is let m be the smallest integer such that you have a linear combination, right? So you have b0 times the identity plus b1 times the first power of the operator, and then you have b2 times the second power of the operator up to bm t to the m equals 0, and we're going to make the assumption that bm doesn't equal 0. Okay, so we can find the smallest power for which this happens, and because bm doesn't equal 0, we can kind of divide out by bm, right? So we get b0 over bm times the identity operator plus b1 over bm times t up to, I guess, what do I have here is bm minus 1 over bm tm minus 1 plus tm equals 0. So what I'm just doing is making this coefficient 1. Okay, so this is great. What we're going to do now is use these coefficients that show up to make a polynomial. So I'm going to make a polynomial. This polynomial is going to be b0 over bm plus b1 over bm z, all up to bm minus 1, bm z to the power of m minus 1, and zm. So I set this, I find a linear relation among the operators, and I use those coefficients to cook up a polynomial, and then the claim is that this is the desired polynomial. So that's what we're almost in the clear. Okay, so we actually have most of the stuff that we need, right? We already have that pt equals 0, equals a 0 operator, because that's just when we plug in t into this polynomial, we get the 0 operator, so that's good. And it's monic because we cooked it up so that the coefficient is 1 over here. And by construction, it has the smallest degree because we took the smallest m for which we have the relation. So there's only really one thing that we need to prove yet, that this is the only polynomial of this degree. And suppose that there was another monic polynomial of the same degree, such that when you plugged in t, you get 0. And if rt did not equal, I'm looking at the polynomials. If rz does not equal to pz, if these polynomials are different, then when you subtract them, you get a polynomial. This is a polynomial of degree strictly less than the degree of pz, because both of the two polynomials will have the same top term and they'll cancel each other off. And we have to have the property that r minus p evaluated at t is equal to 0. Okay, but this is a contradiction. This is a contradiction because the way that we picked our PT was that it was the smallest polynomial that had the property, smallest degree. It was the polynomial of smallest degree that had the property when you plugged in t, you got 0. So this is a contradiction. So PZ is unique. Okay, so because you have a unique polynomial, you can actually give it a name, right? And so we call this the minimal polynomial. So given a linear operator, the minimal polynomial of the operator is the unique polynomial that exists by the previous theorem. Okay, and here's kind of an amazing result, is that the minimal polynomial of t has to have degree less than or equal to the dimension of v. Okay, and why is that kind of amazing? Well, if you go back to the way we cooked up p, we actually took n squared plus 1 element, and we know that there has to be some sort of linear combination of these. And so it could, in theory, have been that m is equal to n squared. It could have been as large as going all the way out, going to the highest power as possible. But in fact, you only need to go up to the dimension. And the reason is by the Cayley Hamilton theorem, right? Since the characteristic polynomial is monic, and it has the property that when you evaluate it at t, you get 0. That's the Cayley Hamilton theorem. What we have is that the degree of the minimal polynomial has to be less than or equal to the degree of the characteristic polynomial, because this is the smallest monic polynomial. This is a monic polynomial with the correct property, and this we proved was less than or equal to n, which was equal to the dimension of v. So I'm going to pause here, but in our last part, we're going to talk about some properties of minimal polynomials and characteristic polynomials.